Hello everyone, welcome back to Tales of Chemistry. Today, let us discuss something about dilute solutions. This is a class 12 chapter, ISC class 12 lesson, the first lesson. Now, to begin this lesson with, we need to know the different methods of expressing concentration of solutions. Different methods of expressing concentration of solutions. Among this, there are three terms that we need to study. One is molarity. Molarity is represented by capital letter M. And molarity M is equal to, or it is the number of moles of solute, number of moles of solute present or dissolved in 1 liter of the solution. Number of moles of solute present in 1 liter of the solution. So I'm underlining the keywords here. Now, M is equal to N of solute, number of moles of solute, divided by the volume of solution. Volume of solution in liters. So I've just written L for liters. Now, what if the volume is given in milliliter? Then you need to convert it into liter. So that is N of solute by volume of solution in milliliter divided by 1000. So milliliter divided by 1000 makes it in liter. So once again, this is N of solute into 1000. This 1000, I'm taking it to the numerator by volume of solution in milliliter. So that's how we find out molarity of a solution. One of the different terms or different ways of expressing concentration of a solution is molarity. The second one that we should study is molality. Molality is expressed or represented by small letter m. Now, molality is the number of moles of solute. Okay, it's also just like molarity. Here again, it is the number of moles of solute present in 1000 grams of the solvent. Look at the difference. Molarity was number of moles of solute present in 1 liter of the solution, whereas molality is the number of moles of solute present in 1 kilogram of the solvent or 1000 grams of the solvent. So molality is number of moles of solute by mass of solvent in kilogram. 1000 gram is what I'm writing as kilogram. Now, same thing can also be written as N of solute into 1000 by mass of solvent in grams. So gram is converted into kilogram. Okay, gram by 1000 is kilogram, but I have taken 1000 to the numerator. So these are two important terms that we need to know to understand this lesson, solutions. Third term, and very frequently used throughout in this lesson, is mole fraction. Mole fraction. Now, suppose if there are two components. Now, by the way, we will get only binary solution as per our syllabus. Binary solution is a solution which contains only two components. So one will be a solute, one will be called solute, and the other one is solvent. Now, mole fraction is represented by alphabet psi, but you can just write it as x. X of solute is equal to, that is the mole fraction of solute is equal to number of moles of solute by number of moles of solute plus number of moles of solvent. Okay, similarly, mole fraction X of solvent is N of solvent, number of moles of solvent, divided by number of moles of solute plus number of moles of solvent. So, mole fraction of a component is number of moles of that component by total number of moles. Since we need to deal only with binary solution, it's always X of solute plus X of solvent is equal to 1 for binary solution. Mole fraction of solute plus mole fraction of solvent is equal to 1. Now, to begin this lesson with, we need to learn another term, that is vapor pressure. Vapor pressure. What exactly is vapor pressure? Now, if you have a liquid in a container which is closed, okay, you have a liquid in a closed container. Now, even if the liquid is at room temperature, some of the particles from liquid state will move to the vapor state. Now, those particles can again condense because your vessel is a closed vessel. Those particles can condense and form the liquid again. In a while, there will be equilibrium generated. Now, the pressure exerted by the vapor on the walls of the container at equilibrium is called vapor pressure. Okay, now this is just one component I took. I said there is a liquid. Now, suppose if that is a solution, then the vapor pressure due to the solution is equal to vapor pressure due to the solute plus vapor pressure due to the solvent. Pressure of solution is pressure due to solute plus pressure due to solvent. But how do we calculate the pressure due to the solute? Pressure due to solute is mole fraction of solute into pure vapor pressure of the solute. What is the meaning of pure vapor pressure of the solute? Pure vapor pressure of solute is, suppose there are no other components, no other particles are present, but just solute alone is present. So only when solute is taken, only solute is taken in the container, what will be the pressure due to the solute? That is P naught of solute, pure vapor pressure due to the solute. Similarly, partial pressure due to solvent is X of solvent into P naught of the solvent. Pure vapor pressure due to the solvent. Okay. Now, this relationship, that is called Raoult's law. Yeah. So, according to Raoult's law, total pressure is equal to sum of partial pressures. Partial pressure due to solute plus partial pressure due to solvent. Now, again, that partial pressure is calculated by multiplying mole fraction with the pure vapor pressure of that component. Okay, now what if we have a non-volatile solute? Okay, we have a non-volatile solute. What is the meaning of non-volatile solute? P naught of the solute is 0. It is non-volatile. It's not forming its vapors. When it is not forming its vapor, then there will be no pressure, right? So, pressure due to solution becomes equal to pressure due to solute, which is 0, plus pressure due to the solvent. Okay, now P of solution is equal to P of solvent, which is X of solvent into P naught of solvent. Okay, now in the next step, I will replace this X of solvent because we know X of solute plus X of solvent is always equal to 1. Therefore, X of solvent has to be equal to 1 minus X of solute. Now, coming back to the first relation which we have written, partial pressure due to solution is equal to 1 minus X of solute into P naught of the solvent. Open the bracket now. So, P of solution is equal to P naught of solvent minus X of solute into P naught of solvent. Yeah, so I just opened the bracket. That's all. Now, bring this minus term to the left side. So this becomes X of solute into P naught of solvent is equal to P naught of solvent minus P of solution. Once again, I'll just keep X of solute on the left side. So X of solute is P naught of solvent minus pressure due to the solution, P of solution by P naught of solvent. Now, this is applicable in the case of a non-volatile solute. This is a modification of Raoult's law, right? So this is Raoult's law itself when your solute is a non-volatile solute. Okay, now any solution which obeys Raoult's law. Okay, any solution which obeys Raoult's law under all conditions of temperature and pressure, that is called ideal solution. So, what is an ideal solution? A solution that follows Raoult's law. Any solution that follows Raoult's law under all conditions of temperature and concentrations is called an ideal solution. What is Raoult's law? Raoult's law is what we discussed now. Yeah, vapor pressure of solution is sum of partial pressure of individual components, and partial pressure is calculated by multiplying mole fraction with pure vapor pressure. And when the solute is non-volatile, then you have mole fraction of solute is equal to P naught of solvent minus P of solution by P naught of solvent. Now, not every solution is ideal because look at this condition. Whatever is the temperature and whatever be the concentration, solution must obey Raoult's law. Only then we can call it ideal solution. There are certain examples for ideal solutions. One is a mixture of normal hexane with normal heptane. Another one example which you can easily remember is benzene. Benzene with the toluene. Yeah, so these are two examples which are behaving ideally under all conditions of temperature and pressure. Next point that we will have to keep in mind is what are the conditions that make a solution ideal? First of all, when you mix the components, that is the solute with the solvent, during mixing, there should be no increment, no increase or decrease in the volume. As in, if you are mixing 1 ml of the solute with 2 ml of the solvent, the net result has to be 3 ml, exact 3 ml. That's when we write delta V mixing is equal to 0. Similarly, delta H mixing also has to be 0. Now, what does this mean? The reaction between this, solute, when you mix it with the solvent, there should be no heat that is evolved, no heat that is absorbed. It cannot be an exothermic or an endothermic change. Yeah, no heat is to be absorbed or released when you mix the solute with the solvent. Okay, so this is a possible question. What are the two conditions for a solution to be ideal? One, delta V mixing is equal to 0. Delta H mixing is equal to 0. Now, one genuine question that arises is when you mix with, say 1 ml of solute with 2 ml of solvent, it's definitely 3 ml. How can it be more or less? But actually, this total volume can slightly vary from your expectation. That is because, there are some set of force of attraction that exist between the solute particles and similar set of force of attraction exist between the solvent also. Suppose when you mix the solute with the solvent, this particular force of attraction is more. Yeah, so imagine that this particular force of attraction is more than the force of attraction between the solute particles, or it is more than the force of attraction between the solvent particles. Then what will happen? Then, if the force of attraction is more, the particles will come close to each other. When the particles come close to each other, the volume, the net volume of the solution will be less than the expected volume. Then the other case, you're mixing solute and solvent, then the new force of attraction is less. Yeah, the new force of attraction between the solute and solvent is less than the individual force of attraction. So what will happen? The particles move away from each other. When the particles move away from each other, the net volume increases. So that is the meaning of delta V mixing has to be 0. It cannot be more or less than 0. That is delta V, change in volume. There should be no change in volume when you mix the solute with the solvent. Now, another possible question here is graphical representation. Graphical representation for ideal behavior. So in this, what we should do is, let's first draw the axis. All right. So okay, so I am representing here x of solute is equal to 1. What does that mean? I have taken only pure solute as of now. So this axis, let it represent vapor pressure. So when I have only solute, whatever vapor pressure I'm calculating, imagine this is the vapor pressure which I have got. This has to be definitely P naught of the solute, pure vapor pressure due to the solute. Similarly, when I write x of solute is equal to 1, x of solvent has to be 0. Because together that make 1, right? X of solute plus x of solvent is 1. Now, the other end, this represents x of solvent is equal to 1. Therefore, x of solute is equal to 0. So whatever vapor pressure I calculate here, this has to be P naught of the solvent. Correct? Now, when we move from right to left, the mole fraction of the solute is increasing. Now, as the mole fraction of solute increases, partial pressure of solute should also increase, because partial pressure of solute is mole fraction of solute into P naught of solute. So as you move from right to left, gradually the mole fraction, the mole fraction of the solute is increasing. Accordingly, the partial pressure increases. So this line represents the partial pressure due to the solute. Okay. Area under this graph is actually partial pressure due to the solute. Similarly, now left to right when I move, x of solvent is 0, x of solvent is 1. So as I move from left to right, what happens is the partial pressure due to the solvent increases. So this line represents P of solvent. Mole fraction increases, accordingly partial pressure also increases. Now, to find the total pressure, we are connecting these two lines. So this is a straight line. Okay. Now, so this top line represents P total. P total is nothing but P of a solution, the pressure due to the solution. So pressure due to the solution is sum of partial pressure due to solute and solvent. So this is how we represent the ideal solution graphically. Vapor pressure against mole fraction. This is a vapor pressure against mole fraction. Okay, so let us change the sign for against. Yeah. Pressure against the mole fraction graph for ideal solution. So this is the graphical representation of an ideal solution. That's all in this video. Stay tuned. Thank you.